Hello everyone, today I'm going to show you more or less live a little experiment involving the hot plate of my Ultimaker. I'm basically just using it as a hot plate here, not really the rest of the printer, a thermal camera and some aluminum powder, and what we're gonna do today is measure the thermal conductivity of this aluminum powder. And as a rough estimate, we can start doing that by seeing how quickly the heat from the bottom spreads into the aluminum powder that, of course, we can also measure in here. And aluminum powder is rather interesting, or powder in general is rather interesting in this aspect, because aluminum itself, and I've added a little solid aluminum heatsink here for a reference, just for comparison, is rather conductive in terms of heat. It is really good at conducting heat, around 200 watts per K per meter, which is rather complicated to convert because you've got several meters in that unit. You've basically got square meters divided by meters, which ends up being just meters. But it has a relatively high thermal conductivity, and you can see that within a minute or so this heat sink is getting rather hot. Of course, it's never going to quite reach the temperature of the hot plate itself, because there's more surface on it. The air is going to start cooling it off the top again. But if you look at the aluminum powder, it's a lot colder, and you might think, because aluminum powder is basically a mixture of aluminum and air has a much lower thermal conductivity, about 1/10,000th that of aluminum. You might think that it's something like an average or so, that aluminum powder would have half the thermal conductivity of pure aluminum. But if you look at these values and compare them, I mean, our surrounding temperature is somewhere around 20 degrees or so. Somewhere around 20 degrees. And if you look at these temperature values and compare them all, that doesn't quite add up. And that's pretty interesting. Geometrically, it's a little bit more complicated. There's no real uninterrupted line of aluminum through that aluminum powder. As there are empty spaces filled with air in between, the heat that goes through aluminum also has to take breaks and go through air for a while. So calculating the actual thermal conductivity of a metal powder filled with air is actually surprisingly complicated. You can get a relatively good mathematical model for a perfectly spherical powder, where each little droplet of powder is perfectly spherical. And there you'd get the result that it should be around 2 or 3 times as thermally conductive as air, which is really low compared to aluminum. But this isn't perfectly spherical. This is just simple aluminum powder I bought. It's mostly in a somewhat chaotic, flattish form, so it's really hard to simulate how well it would conduct heat other than through experiment. Of course, it depends on other outside factors. For example, the pressure applied to the aluminum powder is important, because if we go back to our spherical aluminum powder example, if you apply pressure, the single bits of powder will be pressed flat where they touch each other. They'll have a higher surface area touching, and thus they'll conduct heat much better. And of course it depends on the temperature, because thermal radiation doesn't scale proportionally to temperature. So depending on how high the temperature is, the actual percentage that thermal radiation between these bits of aluminum powder does for the overall conductivity changes. So it's rather complicated, but through an experiment you can get a good idea, and you can see that it's slowly warming up at the top, while at the bottom it's already much warmer. Meanwhile, the heatsink is now almost as hot as the hot plate it's standing on. But this is spreading rather slowly, and we can do a rough mathematical estimate of the thermal conductivity now. Now this is about 2.5 centimeters high, So that means per square centimeter, and aluminum powder is of course also less dense than pure aluminum. This is a little bit over 1 gram per cubic centimeter, so that's about 2.5 grams per square centimeter, since it's 2.5 centimeters high, which gives us a thermal capacity. I'm not entirely sure, but I think it was a little bit over 1000 joules per K per kilogram. So the thermal capacity of roughly 3 joules per Kelvin per square centimeters. And we see it's taking over 5 minutes to reach even a remotely comparable temperature to the hot plate it's standing on. It's still about half, so we can say you should do an actual exponential equation here and use Euler's numbers and so on, but roughly speaking we can say it's going to take around quarter an hour, 1000 seconds to reach the same temperature. Of course it's never going to actually reach that same temperature, but as a linear tangent it's roughly at that rate. So that tells us that in 1000 seconds it's reaching the same temperature. So that gives us the ratio of heat capacity and heat transfer rate, which means since we're at 3 joules per square centimeter per Kelvin and 1000 seconds, that means 1/1000th of 3 joules per square centimeter per Kelvin, so 0.003 watts per square centimeter per Kelvin. And of course this is going over a depth of 3 centimeters, so over a depth of a meter, to convert it back into our original unit, that would be 0.1. I'll have to do these calculations more precisely once I actually evaluate the experiment, but just for explanation's sake, let's say 0.1, which then over 10,000 square centimeters per square meter. No, it should be less. 0.0001 over the 10,000, so that is roughly 1 watt per Kelvin per meter. So it's right in between the thermal conductivity of air and aluminum powder. It's higher than that of perfectly spherical aluminum powder, but as you can see, this conducts heat much worse than this thing, which is already about as hot as the plate it's standing on, while this here is just, at the very bottom it's just as hot, but then it very quickly dwindles down to a little bit over room temperature. So I hope you found this short little introduction or short experiment somewhat interesting, and as always, thanks for watching.